Hello family, as normal, here's Mr. Kuseko again. We're just going for charging and discharging of the capacitor. So talking about how the capacitor can be charging and discharging. Initially, in the first video, I talked about how the capacitor should be charged, the system, the structure. So we said kwamba capacitor kuwa charged, manake the positive should be to the positive and negative should be negative. And when I was talking about the energy, I said the energy stored is always due to the work done against the repulsion when adding the electron to the negative, because the negative is connected to the negative plate of the capacitor and the positive plate of the battery is connected to the positive plate of the capacitor. So electrons are added to the negative and are removed or withdrawn from the positive, are added to the negative, are withdrawn from the positive. So there must be a work done to deposit the electrons, because the negative plate of the capacitor will repel to the electrons, and withdrawing from the positive because the electrons will be attracted to the positive. So speaking about how we charge and discharge, you need to know how is it being connected. So speaking about charging of the capacitor, na wakumbusha tulikuwa tunasema hivi, capacitor ndio hii tunaiweka hapa, tuna connect kwenye negative. That's normal condition bro, that's the normal condition. We connect the positive plate kwa positive plate, kwa negative kwa negative. So what happens, capacitor yenye capacitance C, manake electrons zinatokea kwenye negative potential battery, zikifika hapa manake electrons kuwa added hapa, there must be a work done against, na tulitafuta ndio tunasema the energy stored. Tukapata kwamba energy stored is sawa na a half CV square. I hope you remember about that. Kama hujaangalia hiyo video, nenda ukaangalie mapema then unakuja hapa. Tunaenda sasa, kwa maana hii inakuwa display na huku nako zinakuwa withdrawn. Maana hapa napo kunakuwa na attraction. For that energy to work against now the repulsion and attraction is what we can say is the energy stored by the capacitor. But what's about the charging? Charging lazima positive work kwa positive na negative work kwenye positive. Hiyo ndio nilitaka tuongelee hapo kidogo kuhusu charging, kwa bwana hiko inakaaje wakati wa kucharge. So inaconnectiwa kwenye battery alafu inaanza kuflow, whether tumekuwekea na resistor fulani hapa. So charging of the capacitor actually when you connect a battery source with the certain V, but una connect na resistor na una connect pia na capacitor. That's how we charge the capacitor. So passing through a certain resistance, umeme ukiwa unapita kwenye resistance fulani, maana yake utaichaji capacitor hii. So speaking about that, we can say okay, we can say, talking about the voltage now supplied by the cell, voltage is just equal to V across the resistor plus V ambayo ita drop kwenye resistor and that which will be dropped at the capacitor. So speaking about the V actually, but you know exactly who is V passing through the resistor. Passing through the resistor, the current is always IR according to ohms. But passing through the capacitor, the current is passing through the resistor, the voltage and the voltage across the capacitor is always charge flowing across, but over its capacitance is what we can get the VC, the voltage across the capacitor. To get the total voltage now, V, now we can just display V is just equal to VR plus VC. So what is VR? We can say, okay, what is this? This is the total voltage equal to, what is this? VR. VR is IR, but plus who is VC is Q over C. Oh, what is happening? We can just say who is current? Current is just equal to charge flowing but per time. So we can just say V is equal to dq over dt, then R, but plus Q over who? Over C. So what can we speak about this? we can say times the C times the C times the C. So we can say CV is just equal to dQ over dt. Then who is this? This is R multiplying by C to cancel out the C effects. So this is C, then it's just equal to plus Q. Oh, let's connect the right terms, correct the right terms, and then we integrate it to get the factors from when the charge was 0 to final charge Q at a given time 0 to time T. So let's find about that. Let's find about that. Then we get the net charge at any time. So come you have just charged your battery for how much time? So we can just get over this time we can get this battery, this capacitor storing this amount of charge. So let's start about this. So we can just correct the right term so as we may integrate to get the values. This is Q, then CV minus who minus Q, but this will be this will just be equal to, let me say this is C. Okay, let me correct them as fast as possible. Let me not meander. Let me not meander about this. Let me say, okay, this is CV. When this comes this way, will just be CR dQ over dt. Then is equal to this one goes to that side, so this minus CV. So speaking about that, we can just say this dQ. Let's correct because this is the charge, this is the charge. So Q minus U C V. Then this one will just be equal to, this becomes dt over who CR. But you remember, this came to this side and this went to that side, so this was negative here. So this is negative here. So speaking about that, we can just say, I can integrate these values of charges from 0 to final charge Q. And then I can integrate that time from 0 to time T. So speaking about that, I can just say, this will be the ln of who? Of Q minus CV, then but from 0 to who? To final charge Q, isn't it? Speaking about that, we just be having this is negative T over CR. Wow, because this one will just be from 0 to T, so minus 0 is just the negative one, T minus that one. But you know, this is ln of Q minus CV over who? 0 here becomes negative CV. So minus is just the division in terms of ln, the natural logarithm. So about that is negative T over CR. So we can just speak about this. We can say, okay, so this is Q minus CV over negative CV is just equal to negative T over CR. So the ln becomes the L right to that side. This is ln base E, log base E. So we can just say Q, the charge now at any time T. I said from 0 to final, meaning at time T. So this one will be, when this comes to that side, it becomes the positive CV, then minus negative CV, then E, negative T over CR. So speaking about the charge at a given time, but this CV was the initial charge, due to the potential in the capacitor and the capacitance of the capacitor, the potential and the capacitance of the capacitor. So we can just speak Q at any time is just equal to the initial, but 1 minus who? Minus E negative T over CR. That's what we can say about the charge at any time T. Charge of the capacitor at any time T when charging. So when charging now, when charging a capacitor, really, when charging the capacitor is always connected to a resistor from the source, so as charge at any time. So there are cases here. Questions comes depends on the cases. They can ask you the charge at any time. They can ask you now the questions, or let me say the cases to consider. To consider now. one of the first case to consider is they can ask you cases like what's the charge at time t? Charge at a given time. They give you a time. So the charge at a given time is just given as Q is equal to Q naught, then 1 minus who? E negative T over CR. That's what happens. So speaking about that, they can just ask you to draw the graph about this. So when you see the graph 1 minus, it's always, so you can just say that's its graph, and this is the logarithmic natural one. So this is the Q, but in relation to its time here. So this is the final charge Q. So the graph of Q against the time will be just be the graph for that equation. Wale PCB sasa, you just ngoja niwasaidie hapa wale PCB, look here. Zile final charges for those PCB, look here. The nature of the graphs. When you see something like y is equal to AE negative x, the L light, you can just draw it as this one. When you see y is equal to A but 1 minus E negative x, this should be reversed. It should be reversed like that. Like this one. When you see, for example, is y equal to A, then let's say A and then negative E negative x. You draw it as the negative, like that. You see it? Yes. So there are those three nature of graph that you need to know about the natural logarithm graph, natural logarithmic graphs. In case it is negative, you reverse the values. In case it's just positive 1 minus, you just use it. In case of it's just the positive here but the negative x, you just draw it in that nature. So let's continue. You can be asked the charge at any given time t. At any given time t. Okay. So we can say charge at any given time. They can even ask you number 2, the voltage across the capacitor. Voltage across the capacitor. Voltage across the capacitor. VC is just equal to Q over C. What's the charge at any time? So VC is just equal to Q. What is Q naught? We said is CV, then over C. 1 minus E negative T over CR. So what happens? C and C cancels. Then V across the capacitor is just equal to V. Then 1 minus E T over CR. That's what happens. So speaking about number 3, we can just say about this, the voltage across the capacitor, but also we can just speak about the voltage across the resistor. Voltage across the resistor. We said as we are charging the capacitor, let me draw for you here. Let me remind you about this. When we are charging the capacitor like this now, when we are charging the capacitor, the example is, it's like we had this drawing. This is the capacitor and this is the cell now. This is voltage. We had a centennial resistor here. So we said V is just equal to who? VR plus VC. The potential from the battery is just equal to the summation of potential drop here and the potential drop here. Then we get this one, isn't it? So we can just say, okay, the voltage across the resistor, if we have the voltage across the capacitor, we can just say the voltage across the resistor now is just equal to the voltage from the battery minus the voltage of the capacitor. So VR is now equal just to V. This is just equal to V. C is just equal to V minus V E T over CR. So we can just this minus this. So we can say V, but minus who? Minus V, then plus who? V E negative T over CR. That's what happens. The velocity, the voltage across the capacitor. So this one and this one cancels, while this one becomes the plus. So we can just say, okay, this is 1 minus. So we can say the voltage across the resistor is just equal to V, but E T over who? Over CR. That's what happens. That is what we can say the voltage across the resistor. How about its nature? How about its nature? The graph for this one, you can just draw according to its nature. The VC with the time. How about the voltage across the capacitor? This I told you about this. If you have this nature, you just go around this one, and around this one, and this one will just be the maximum V. Speaking about, let's say about this. If I have this, the nature for this, let's draw about the nature for this. The nature for VR, voltage across the resistor. I say if this is just the negative, so we can just speak about this as over time. So this is voltage across the resistor, but this maximum here is just the V across the battery. That's what happens. Let's speak about the instead of the voltage. They can also ask you some questions like the rate of flow of charges, meaning the current flowing as it is charged, as the electrons flows from the battery to the capacitor. Rate of flow of charges. Rate of flow of charges. Let's speak about the rate of flow of charges. Rate of flow of charges. Speak about the rate of flow of charges. Speaking about the rate of flow of charges, number 4, cases. Those are the questions coming. Cases to consider are the cases now. Rate of flow of charges. Rate of flow of charges. So the rate, speaking about the rate of flow of charges, meaning current is the charge flowing per time. So speaking about the rate now, is the change, is the differential for who? For CV, then who? Minus CV E T over CR. That was the charge we obtained over the T. So we are differentiating with respect to time. So the current on differentiating, so this one will just be constant. So CV, so will just be 0. But this one will just be negative CV who E T over CR. Differentiating the constant is just equal to 0 now. This because this one is just 1. So speaking about this, CV remains, but this one comes to this way. Will just be brought that, so C over R. So about that, C and C cancels. So current will just be negative who? V over R, but E who? T. This one was negative, and this one coming is negative. So it becomes the positive. The positive, because it's negative 1 over CR. We are differentiating with respect to time, so becomes the positive here. So speaking about that, that is T over CR. So speaking about the rate of flow of charges will just be equal its nature now. The nature for the graph. This is the graph now. Graph of the rate of flow of current with the time. So the rate of flow of charges over time. Graph. So what's about the graph now? We can just draw like this now. This is the rate of flow of charges. If charges flowing per time, but over time. So when we are drawing about that, the current over time, its nature will just be, so the rate will just go on increasing. While here it's just what? V over R, the initial current. We can say this is the initial current here, or this is the current flowing at a given time. The nature of graph, I told you there as the first time. So speaking about that, we can just say, oh, god damn, this is ridiculous. So we can just say, oh, speaking about the rate of flow of charge, this is the graph for. But how about if they ask you things like they ask you not the nature, rate of flow, they can just ask you in two cases. They can ask you instantaneous, instantaneous. This one is the instantaneous at any time. Instantaneous, instantaneous, meaning at any time, at the given time. But how about, there are three cases. How about if they tell you about the initial rate of flow of charges, meaning at initially when you are starting to charge, meaning time is just equal to 0. So speaking about the rate now, we can say I is just equal to V over R, but who E T over C R. So time is 0 now. When you take your calculator and put the you put the shift then to the run, and then you put the 0 here, you get 1. So if this one is just equal to 0, this one is just equal to 0, so what happens? This becomes 1. So the initial current initially at time 0 will just be equal to V over R. That's the initial flow, rate of flow of charges, meaning the current. How about if it is not the initial, it's about the final, let's say at infinity, because the capacitor can be charged to a larger time. So speak about the case number 3 here. Speak about the rate. They can ask you, find the charge stored at infinity, the rate of flow of charges at infinity, meaning at time is very large. Time is very large at infinity. Infinity. So speaking about that, you can say the rate of flow of charges is always equal to V over R, but who E, this becomes, if the time is very large, meaning negative T over CR. If time is very large, this means the whole thing becomes the infinity. So negative infinity, put your E power number, power very large number, this becomes just equal to 0. So all of this cancels. So you get the dq flowing per time is just equal to 0. Even put mara, you just put, for example, here I can just say, okay, this is shift, then EX, then I put even F-tano. Let me say F-tano. No, let me say E, then E, then let me say na F, oh, math error. Let me do the alpha, then E, and then let me say 45. Oh, still yet? God damn. This to the infinite, I don't know what's the problem now. Let's go on. So when you put the very large number, is always giving you to 0. So speaking about the rate, will just be equal to 0 at infinity. And meaning the rate be, do you get this? I don't know if you get this concept. If the capacitor now of centennial capacitors having a centennial resistance, and then the rate of flow of charges, meaning the charges flowing per time, is just equal to 0. This means this capacitor is fully charged. As since it contains the dielectric material, it limits the flow to the other side. So meaning that is what it means about the rate of flow of charges. Those are the cases that we needed to consider. Okay, let's continue, guys. That's what happens when in terms of the questions. So they can even ask you how to calculate the heat generated after time. So speaking about the heat, let me for example do here about the heat. Let me for example do here about the heat. Heat after time. So heat generated after time. Number 6. 6 questions that they can ask you. Heat generated. This physics is so easy, guys. After time T. So what happens here is we say heat is just equal to I square RT. Oh, so speaking about that, we know the I, who is heat is just equal to RT, but who is I? I is, we said V over R, then E negative T over CR. That's why we can say squared. So speaking about that, this will cancel with this one. So we have V T over R, but this is square. While this one comes to be E, who is negative 2T, the square inches over CR. That's the heat generated after a time. Heat generated after a time. ITV or IR square. IRT. That's what we can say. That's what we can speak about the heat generated over a time. Okay, so let's speak about discharging of the capacitor. How to discharge a capacitor? Discharging of a capacitor. Discharging of a capacitor. When the capacitor have the capacitor, let's say this is the capacitance here, and we have here now on discharging is you just connect the capacitor with the centennial resistor such that the energy that was stored in the capacitor should be dissipated in the resistor. So we need to have a device consumer, or we call a rod. So a resistor here, a resistor. That's how we discharge. That's how we discharge now without a supply of the energy from the battery. So when you connect it with the battery, that is charging. But when you omit the battery, that's what you can call discharging. So we connect it in this way, discharging of the capacitor. So what happens? The voltage from the capacitor is the one being discharged as across the R. So the energy stored by the capacitor is the one being discharged. So you put the negative, meaning discharging. There is an increase in actually the potential of the capacitor as the charges are increased. So speaking about that, we say what is this charge? Is across the capacitor. What is the voltage? Is the Q over C. What is about this? This is just equal I times R. So speaking about that, we can just correct the right terms by saying this current is just equal rate of flow of charges as current across the resistor times R. Then this is just equal to Q over C. So I can just correct the right terms and integrate it from initial time when the charge was a final charge. Hey, goddamn, get this clear, guys. In charging, we started at 0 to the final charge Q. But now we are doing the discharging. So the initial charge should be the total charge. Hi! And the final charge will depend on the time. It can be 0. But the first thing you need to know, on charging, we start with 0. But on discharging, we start with the final charge. So let's or the total charge which was stored initially. So let's speak about this. Physics is so sweet, guys. God damn. So let's talk about this. I can just correct the right terms and say this CR and this time becomes the so we say the then this becomes this one, so dt negative dt over CR, then I just have equal to dq over who? Over q. So speaking about that, I integrate from 0 to the final charge q. Let's say q naught. From here 0 to time t. So speaking of that, it will just be negative over CR, but it's just equal to, who is this? This is just equal to the rho now. So rho of who? Of q over q. So speaking of from 0 to q naught. Oh, what happens? So what is happening? Meaning, let's say from 0 to time t. Meaning, this, let's say this is the initial charge, but the final, let's say the q at a given time. So I'm taking this, I'm discharging from initial q naught to the final q. So hey, not this. Before I just move on. This one is the final, let's say a charge at time t. Q naught is the charge at initial, or t sawa 0. Initial charge, initially charge initial. at time t is sawa na 0. So speaking about that, I can just say okay, I can only speak about that. I can say I can just say this ln E T over CR is just equal to, who is this? Ln of Q over Q naught. So speaking about this, hey mama kai, this is negative without, so so when I raise this, because this is a log of E, you can say E T over CR is now equal to Q over Q naught, the original. So I can just speak about the Q. The charge is just equal to Q naught, which is equal to E T over CR. So we can just say, we can just say about this, we can say this is the charge at a given time. Charge Q is the charge at a given time t. So we can say, okay, if they ask you about the rate of flow at a given time, number 2, this is number 1. So how about the nature? You know about the nature now. You remember about the nature. What's the nature? This will be, this is the charge, this is the time. So since it is just the negative there, negative exponential. So how about if the charge, that's the charge at the given time t. So how about we speak about the, let's say the rate of flow of charge flowing per time. That's what you can differentiate this one and say what is Q naught is CV. So it's about the differential for who is CV, and then E negative T over CR, we differentiate it with respect to time. So that's what we say CV, but who is this? It's negative CR, then there's E T over CR. So cancelling the C's, we can just get, we can easily get the V. So speaking about the rate of flow, rate will just be the V over R, then E negative T over CR. That's what we can speak about the rate of flow of charges. How about if we speak about the that's about the rate. Number 3, we can speak about the and this, there are 3 cases actually. Initial instantaneous, this is the instantaneous, meaning the current at any time t, at any time t. Initially, meaning current at I naught, and final, so the final current, the rate of flow, meaning at infinity, the rate of flow at a given time, very large time. So speaking about that, we can just say, oh, let me speak about this. Let me speak about this. You know now about this. Let's speak about these things. So about, we have just spoken about the rate. We have just spoken about the nature of the graph. We have just spoken about it. How about if they ask you voltage across the capacitor? We know voltage across the capacitor will just equal to Q over C. Oh, what is it? This is the Q. Q we obtained is just equal to CV, then E negative T over CR. So we can say this is just equal to V, because C and C cancels. C and C cancels, E negative T over CR. So cancels and cancels. So the V across the capacitor is just equal to V E negative T over CR. That's what happens. How about the, let's say the voltage across, this is about the voltage across the capacitor. How about the voltage across the resistor? voltage across the capacitor is just equal to negative voltage across the resistor. So voltage across the resistor wanna be negative V from the cell actually E, yeah, T over CR, the initial. So that's what happens, the negative. The nature for this will just be, this is negative exponential, so it's always this time, and here is voltage across the capacitor, but here the final was the V, the initial one, the initial voltage. How about this? This one, the same VR, while this one is time. So because it's negative, you reverse, guys, you reverse. Now the graph will look like this. The graph will look like this. This is the voltage VR, and now it will just look like this. This is the V, while this one is time. So the graph will look like that because of the negative here of the exponential. So the graph will just be reversed. That's why we can just speak about the charging and discharging of the capacitor. Charging and discharging of the capacitor. So generally, if you forget about everything, don't forget about these two formulas. Don't forget about these two formulas. Don't forget about these two formulas. When he's speaking about everything and forget, so speaking about the charging is always the charge equal to CV1 minus E negative T over CR. But discharging, everything comes from here. It's just equal to Q at a given time. It's just equal to CV but E negative T over CR. That's what happens. What happens is the same thing. Okay, this is Kusekwa. I'm signing out. That was charging and discharging of the capacitor. See you. God dang. And then capacitor is over. So I'm just going to finish about the waves, about the wave motion, the sound, and the Doppler. Thank you guys. It's Kusekwa, your boy. Let's see on December, and Preform 5 is about to start on January. We shall have the total online course, but also we can have the physical course at Perfect Vision with the other teachers. But also I'll be there in every program for solving the questions. I love solving. I love solving questions. I like to discuss the consequences, the problems, like how about this happens, about how about why this, what about. I love solving, guys. So it's Kuseko, boy. I'm signing out. Make sure we meet out. Say hi to me whenever you see me, that I may get encouraged, and I'm just so happy about. Woo! God damn it! It's like so fun in this 55. Okay, see you.